already 15 minutes, right?
Yeah, 15 minutes. Yeah. 1 minute. Okay, guys, so I suggest we slowly start. So it's my pleasure to invite Professor Alex Matos-Abiaga from the Wayne State University in the United States. So Alex is visiting the NCKU on the premises of the program 100 Years of Success of NCKU. So he will be staying here for 6 weeks. He's giving this mini course about the Spintronics. But if you would be interested to talk with him, because you like the topic or something like that, just let me know. I think we would be very happy to talk with you or share or tell you something more. And about Alex, so Alex finished his PhD in 2004 in Germany, in the Max Planck Institute in Halle. And then I think we met together in Regensburg because we were together in the group of Professor Jaroslav Fabian. And then I think in 2014 you finished and you moved to the United States. And first Alex was working in the University of Buffalo as a research professor, and from 2017, I think, Alex is at the Wayne State University first as associate professor, assistant professor, and now as an associate professor. So let's give Alex a very welcome. And I think take it as a lecture. It would be pedagogical, I think. And I think if you have questions, you can always ask, and let's make it a live of the time of the show. Okay? Thank you.
Okay, thank you, Dennis, for this nice introduction. I'm very happy to be here today. And as Dennis mentioned, so if you have any questions, just please raise your hand, and you can interrupt at any time, so that's okay. So this series of lectures, so there is a very short course about the Spintronics. Spintronics in the last 30 years or so have become actually a very wide topic. So so we actually will need several courses to overview the whole Spintronics. So I have selected some topics, and so I will go through a little bit. I will give you an idea of more or less what we have in this course. So these are going to be some selected topics in Spintronics. Some of them are from the early days of Spintronics. The other ones are more contemporary. So the idea of Spintronics actually is not new. This is already coming from about 30 years ago or so. And the big motivation for this was essentially the challenges that electronics was facing at that time. So when I say electronics, I mean charge-based electronics. So mostly
Pointer.
So I think I have here.
Okay, good.
So when I say electronic, I mean charge-based electronics. Most of our electronic devices nowadays are using the charge of the electron, so only the charge of the electron. So these are charge-based electronics. So one of the problems is we have been trying to do these devices smaller and smaller. The smaller you make it, so the faster they get. So the more power you can, the more powerful the devices become. But there is also a problem. One of the big problems is heating and power consumption. So at some point, just to make it too small, and they start to dissipate a lot of heat. So you need also a lot of power consumption just to cool down these devices. So another problem is the increasing of the cost. So anytime you want to make these devices smaller, so you have to change technology. So you have to invest a lot of money, for these industry updates and so on. So someone said we will run out of money before we run out of physics, and probably is very true. So ultimately, there is a physics limit to this miniaturization. So eventually, we may need to change actually the rules of the game. And so one of these ideas to overcome for this problem is to use quantum computers. So here are the possible way out. So one of them is to improve the performance by optimizing the device architecture. This is what the industry prefers because it's not so costly, but also give you a solution, a short-time solution. Okay? Then we can revolutionize the hardware. So by implementing new alternatives, and one of them in that case would be, let's say, Spintronics. And so the other one will be to revolutionize both the hardware and software, which will be essentially the idea of using quantum computing. So this Spintronics and quantum computing are probably come to as a complement to electronics, not really to substitute electronics, but will be improving electronics in some areas. So the idea of the Spintronics, as I mentioned before, came quite a few years ago, and the idea was, okay, so electrons have charge, which is what we use for conventional electronics, but we know that electrons also have a spin, so why not using the spin of the electron to do some sort of electronics? So electrons have charge, have a spin, so they are like a very small magnetic magnet, so they have a magnetic moment, which is a spin, and we know that the projection of this magnetic moment can have two values, plus minus h bar over 2. So the magnetic moment then is essentially proportional to this to the spin. Okay. We can also use this, the spin for doing logic, because we have these two states of a spin. So we can use, let's say, spin up like a 0 state and spin down for the 1 state, and we can also use spins for do quantum computing. So what are the natural advantages of using the spin? So one of the very important advantages is low energy consumption, and the thing is much more, you need more energy to move the charge of the electron than to flip or manipulate spins. So this is one of the big promises of Spintronics, is to lower the power consumption of the devices. Non-volatility. So this was a very big issue 30 years ago, especially for memories. Nowadays we have flash memories. They are also non-volatile, but still they are slow. So you want to use non-volatile memories in the processing period. So you really need probably to go to Spintronics, because the flash memories are not going to do the job. So it also allows high integration between logic and memory, because you can use the spin for logic and memory at the same time, so they don't need to be separated, these units, so you could integrate the units and save a lot of energy also, so because you don't need to communicate constantly the processing unit with the storing units. So the other thing is higher speed, so the spin dynamics itself is much faster than the dynamics of the electron moving around in the materials. So I have a couple of reviews here. So these are reviews on Spintronics, especially this second one is a little bit like a book. It's large and very pedagogic, so you are interested in going further in this topic, so you can have a look at this review. It doesn't cover anything, the new things. You see it's 2007, so there have been actually a lot of new things coming out in this field, which, well, are not in this review. So here is an example of the power of the problem of power consumption, and this is, data for Microsoft Storage Center in Norway. So Norway is a very cold place, so you probably need not so much power to cool it, at least in the winter, but you can see this power consumption, and I just look at the data, compare the power consumption to the power consumption of the Tainan city, and it's 4.5 terawatt per hour, so which is smaller, but still, for a single data center, it's a lot of energy. So Microsoft have hundreds of this data center, and the power consumption is really high, and it's going to be increasing now with all this, storage with the artificial intelligence and so on. So that's why cutting this power consumption is actually very important, and hopefully Spintronics can provide an alternative to improve this situation. So one of the first, or perhaps the first device really that make an impact in electronics coming from Spintronics is the so-called giant magnetic resistance. So GMR is giant magnetic resistance, hard disk drive, red heads, and sensors. So this actually, it's very interesting because it was discovered in the lab, and it was in almost every computer in a period of just 10 years. It's probably one of these phenomena that have gone faster from basic research to applications. So nowadays, we have improved this effect, and this GMR is not used so much. So I have been substituted by some other effect, which is called TMR, is tunneling magnetic resistance, because the effect is actually higher than this GMR, so it's more effective. But the idea comes essentially from this GMR device. And so the people that discovered the GMR actually got the Nobel Prize for this. So, since the initial days of Spintronics, and it has been growing and growing this field, and it's becoming a very multi-field actually. So you have a lot of fields connected to this Spintronics, and we have a spin and Spintronics. We have photons because we can manipulate the spins also with light, and we have also electronics. So we have these three sources here: photon, spin, and electron. And we have crossover between all these fields, so it's highly multidisciplinary field with a lot of things. Actually, there are few other things that we could add here, like topology and two-dimensional materials and so on, which also provide new platform for Spintronic application. There have been a lot of devices. I just put in here a few of them. So most of these devices are actually in a prototype. So especially these ones here, so the spin LEDs, thin solar cell, photodiodes. These here actually are already in the market, so they have actually a lot of use in the market. The other ones are mostly prototypes, so they still need to improve the efficiency and the cost, right? Because it's not only efficiency, you need also to lower the cost of this production so that it becomes relevant technologically. So, having said that, let's go to the roadmap of this course. So these are the topics that I have selected for this course. So we have the topic of spin polarization, spin current, and spin torque. That's what I'm going to talk today. Then we will have effective mass, effective G factor, and spin orbit coupling in semiconductor heterostructures. We'll have magnetic tunnel junctions and tunneling magnetic resistance. Then some basics of BCS theory of superconductivity and the Bogoliubov-Dejean approximation. So we'll go, after that, we'll have an analysis of how to classify matter according to topological properties, and especially several symmetry classes, and to classify the matter. And we'll discuss it within some detail, the phase of topological superconductivity, and what is important, what it can bring to as applications. So finally, if we have time in the course, then we will talk also about Majorana-bound states. So these are states that have very exotic properties and maybe are potentially useful for topological quantum computing. So we'll talk about, if the time allows, so we will actually talk a little bit about these Majorana-bound states, how to produce them, how to detect them, what are the signatures, and how to use them. So in the philosophy of the course is that I will give you mostly ideas. So I will go also through some math. So I will, but most of the math I will go actually fast on that, and I will give you the notes with the math so that you can use this at home. I have also a collection of problems. You can use this problem also to exercise yourself. So for today, that is what we will have. So we'll have spin polarization, spin current, and spin torque. So I will be introducing the spin first. So the electron spin, I will refresh a little bit the idea of the spin. We'll review a little bit how it was discovered and how Pauli introduced it, how it is related to the so-called SU2 symmetry, and how it also, how these Pauli spins are related to the Dirac spins. So I will make some comment that sometimes you actually don't find it in the books, but you can get this from these books. So then I will discuss a little bit about spin polarization. I will introduce the concept of a spin polarization and exchange splitting. So some ways of achieving this spin polarization. In particular, I will discuss exchange splitting, and then other ways of inducing spin polarization like a spin injection and spin extraction, and also other ways like magnetic proximity effect. So these are several ways of how to induce spin polarization or create spin polarization in materials like, let's say, like in semiconductor, which most of them are non-magnetic, so there is no spin polarization in most of them. You have to create them, right? So I will discuss some of these methods. Then I will go through a derivation of the spin continuity equation, and from this spin continuity equation, you will get the definition for a spin current. So in the same way we have charge current, so we can also have spin current. So they are different, and there are some issues with the spin current, so I will go into some details in there. And we will also have the concept of the spin torque. And so not today, but in other lecture, I will talk a little bit more also about the spin torque. Today, I just will introduce the concept. So how the spin or the concept of spin evolved. So it actually started in 1897 when Thomas Preston measured the anomalous Zeeman effect. So the Zeeman effect was measured by Zeeman the same year, so 1897, and a little bit later, Thomas Preston measured the anomalous Zeeman effect. So they call it anomalous because they didn't know what was the reason for that. So in the Zeeman effect, so you have a splitting in the atomic spectra when the atoms are exposed to a magnetic field, and this splitting actually comes from the orbital angular momentum. So the electrons are forming current loops around the atom, around the nucleus. This current loop generates a magnetic moment, and this magnetic moment interacts with the magnetic field. So this is essentially the origin of the Zeeman effect. Now, when Thomas Preston did the experiment, what he observed that apart from this, there was an extra splitting, and they didn't know where this splitting comes from, so they call it anomalous Hall effect. So everything that you don't know what is the origin, you call it anomalous, like the Hall effect, then they come the anomalous Hall effect because they didn't know what was the reason. So this problem stayed there for a while. And then in 1921, Landé provides an empirical explanation for this anomalous Zeeman effect. It's empirical, so it just makes some formula, just base it on the result, but without physical insight, actually. So in 1922, Stern and Gerlach did an experiment, and they, without knowing, actually measured the spin. So they were given the Nobel Prize some years ago, after that. But when they measured the spin, they were not actually measuring this, or not knowing, they didn't know that they were measuring the spin. So what they saw that they were measuring was the space quantization, essentially the quantization of the angular magnetic moment, or the orbital angular magnetic moment, not the spin magnetic moment. Okay. So there is a very fascinating story of how they discovered that, and I encourage you, all of you, to read this story. It's very funny, very entertaining, full of coincidences and circumstances, so it's really unbelievable how they discovered this. So here, it's a link. You can go to this. It's in article in Physics Today, and it's really like a Hollywood movie, this story about the discovery of the spin. So you can already see the title of, which is not, it's a little bit surprising that there is some cigar involved in all this story. Okay. So in 1925, then Ralph Krionig, which was a student at Columbia, PhD student at Columbia, proposed an idea a classical idea for this spin magnetic moment. And this, he assumed that the spin is rotating itself, so it will generate, this loop current, which will generate this magnetic moment of a spin. And this, I think he talked to Pauli to this, and Pauli heavily criticized this idea. So he was, he then actually never published this idea because it was destroyed by Pauli. He also found that actually there was some problem with this interpretation because if you do a calculation of how fast this electron need to be spinning to produce the magnetic moment of the electron, so you will find they have to be spinning like 60 times the speed of light, which will be, of course, in contradiction with the special theory of relativity. So he never published the idea, but coincidentally in the same year, 1925, Uhlenbeck and Goldsmith actually published a paper with the same idea of Krionig independently, so they didn't know about that. And then Krionig said, but I know that this model is not good. So he wrote a comment in Nature criticizing the model and showing that you need this about 60 times the speed of light, the electron to spin in order to get this magnetic moment or the spin magnetic moment. So, but then Pauli actually discovered in 1925 the exclusion principle, and then in 1927 he go back to the problem of the spin, and he published a paper introducing the famous Pauli matrices, which then provided a mathematical framework for a spin. So a little bit later of that, in 1927, then Fraser actually was looking again at the Schrödinger-Lach experiment, and he realized that actually in that experiment that was done, like 5 years ago, so they could not have actually been measuring this orbital angular momentum because they used silver atoms, and in the ground state of silver atom, this orbital angular momentum is 0. So he actually found that, actually they were measuring the spin. So after that, then he opened the door for Schrödinger-Lach to get the Nobel Prize for the discovery of a spin. So here I leave you, like the homework. You can do this at home. It's just essentially to estimate this speed that you will need, that the electron will need to for rotating and generating this magnetic moment. It's a relatively simple problem, and of course it's using all this, classical idea. I will show you later on that it's not so wrong actually. So you just have to do it properly, not just with classical physics, but with quantum, and it have some idea of this spinning is still in there. Okay. So the conclusion is that in addition to orbital angular momentum, elementary particles also carry another form of angular momentum, which is not related to the motion in space. So it doesn't depend on the position variables. It is somewhat analogous to the classical spin, and that's the reason we call it a spin. However, you should take this analogy. You shouldn't take this analogy too far. So this intrinsic angular momentum is what we call a spin, and it's in addition to the orbital angular momentum. So how does Pauli introduce the matrices? So, it's, you have to follow a little bit some logic steps to figure out these matrices. The first observation is, if a spin is a vector, so I have 3 possible orientation, you need 3 components, so you will need 3 matrices. Each matrix, for each of this spin component. And then he knew that that this magnetic moment intrinsic magnetic moment of the electron will have 2 possible values. So the matrix have to be 2 by 2 because it have to have exactly 2 eigenvalues. So they have to be 2 by 2 matrices. So they have to also be Hermitian because it will be like a quantum mechanical operator. And the important thing is also, it's an angular momentum, so I have to, to obey the same sort of commutation relation that angular momentum obeys. So, and this right here you can see the commutation relation for these spin matrices, but that is actually the same commutation relation you would have for orbital angular momentum that we already know. So he just used, okay, I will just take the same relation that I will apply to these new matrices now, which have to be 2 by 2, and we have 3 of them. So when you do that, the orbital angular momentum, so you will get possible values here, which will be just the integer one. But this is because in the orbital angular momentum, you need boundary conditions. You rotate by 2 pi, you should get the same thing. And this somehow impose that these possible values here are 0, 1, 2, 3, and so on, and not with the 1/2. But now, this is an intrinsic, have nothing to do with this rotation of the electrons around the atom. So then he said, okay, I will will not limit my numbers to just integers. It could also be half integers. Okay, with this, and using a basis of, for a 2 by 2, the easiest way is just to get the basis 0, 1, and 1, 0. So he just took this basis, and then he, for this basis, used this commutation relation here. So you can see the action of these operators, how they, on the vectors here, on the basis, how will transform. And then with this, you can find all these properties here, right? So with these properties, then, you just can calculate the matrix elements. You can use all these properties here to calculate the matrix elements, and what you will get essentially these 3 matrices, the Pauli matrices. Okay. So this is explicitly here in this problem, so you can guide you how to get there. So there are some properties of these Pauli matrices. I'm not going to go through all these properties. I listed here because they are useful for doing calculations, so you can have it if you ever need to do calculation with Pauli matrices. Okay. Perhaps one that I would like a little bit to comment is this one, because we will use this one later on when we go to the classification of topological matter. This is operated for spin reflection. So you typically don't find in the book, so I just wrote it in there. So in the books, you may probably find everything from A to H, but this I is rarely written in the books. Okay, so what else, or what other properties fulfill these Pauli matrices? Well, these Pauli matrices obey this commutation relation here. So these, square brackets are commutator. And so they form what is called an algebra. So I'm not going to the mathematical detail, but so an algebra is just something that similar to a vector space, but with some different rules. Okay. Now this algebra, specifically for this case, called Lie algebra because they are non-commuting, and this specific algebra that is there is called the SU2 algebra. And the elements of this algebra, which are the Pauli matrices, they generate a group which is called the SU2 group. I will tell you why I'm talking about all this in a moment. Okay. So what is the SU2 group? So the SU2 group is the group of all 2 by 2 unitary matrices with determinant 1. So all the matrices 2 by 2 that are unitary and have determinant 1 belong to the SU2 group. And they can be generated by using Pauli matrices, so which we have through this relation here. Okay, so the Pauli matrices are here, and these are the SU2 matrices. So unitary matrices with determinant 1. So essentially, it's, if you look at this, it's and some of you probably have been something like that. I've seen something like that before. This is nothing but a rotation, a spin rotation by an angle theta. Okay, along an axis, around an axis n, in the n direction. So this is an operator for a spin rotation, and using the Pauli matrices, you can generate all the elements of this SU2 group. So I will come back to this SU2 symmetry in a moment. So when you incorporate the spin into the Schrodinger equation there is a spin. And so Pauli generalized this Schrodinger equation to introduce the spin. So we see now that the spin is given by the Pauli matrices. And then, so the electric magnetic moment mu is an operator now that can be written in terms of Pauli matrices. So there is an energy, so the energy corresponding to the interaction between this intrinsic magnetic moment of the electron spin and the external magnetic field, so is given by this dot product of the magnetic field and the magnetic moment. And then we also have spin-orbit coupling. So spin-orbit coupling is essentially the interaction of the electromagnetic, the spin magnetic moment of the electron with the magnetic field that it sees when it is inside an electric field. So from relativity, we know that if an object is moving in an electric field, in the reference frame of this object, the object will experience this electric field as a magnetic field. Right? So electric field becomes magnetic field in the reference frame, which is moving in this electric field. So when the electrons are moving in an electric field, in the reference frames of the electron, it will see the electric field as a magnetic field. So this magnetic field then interact also with the spin magnetic moment of the electron, and we have a sort of interaction here. So this is B, and I call here relativity. From relativity, so this B depends on the electric field, because actually given by the electric field in which the electrons are moving. So if you work it out a little bit, so that's what you will get. You can actually get that this spin-orbit coupling interaction transformed into this form here. Lambda naught is essentially a constant, so it's a square over 4 mc square or something like that. And we have here the Zeeman, or what was called at that time the anomalous Zeeman. We now don't call it anomalous anymore, just call it Zeeman effect also. So this is the Zeeman interaction between the magnetic field and the spin of the electron, and here is the spin-orbit coupling in the presence of an electric field. So the electric field here is here in the gradient of the potential. So the gradient of the potential B will give you essentially the electric field. And then we have this Pauli-Schrodinger equation. So I have included also the vector potential action in this. So the vector potential corresponding to the magnetic field also enters in the equation through this minimal coupling in which the momentum have to be changed by the kinetic momentum have to be changed by the canonical momentum. So this is the Pauli-Schrodinger equation, and this is essentially what we will use in most of the in the course. So we rarely need to really go to the Dirac equation or something like that. This is more than enough for treating our materials and so on. So some observations here. The Zeeman, the Zeeman interaction couples the spin to the magnetic field, means I can use magnetic field to manipulate spins. And the spin-orbit coupling couples spin to momentum and to electric field. So it means I can also use electric field to manipulate spins. And this is very powerful because the Zeeman interaction is actually pretty small. So if you look at, you put numbers in there, you will see that this is typically very small. So you will need really high magnetic fields to manipulate spins in non-magnetic materials. But you can actually, we will see that this coupling can be actually relevant at a relatively small electric field. So you can, in practice, use electric field to manipulate the spin. So this lambda naught that is here, which is actually, I told you before, is a square over 4 mc squared. It's also very small. It's just a scale like 1 over c squared. But this is for electrons in vacuum. So when you put electrons in a material, well, we call it actually quasi-electron because it's not just electron moving, it's electron interacting with everything you have in this material. And this constant gets actually renormalized. It gets like 5 to 10 order of magnitude larger than the one in the vacuum. But we will see this in the next lectures. So you can also get this Pauli-Schrödinger equation really starting or doing it properly. So in a way, Pauli didn't do it very rigorously. So he just, okay, I will introduce these matrices, have a logic, of course, but it's not really from scratch. So you want to get it from scratch, you have to do what Dirac did. So the Schrödinger equation is not invariant under Lorentz transformation, so it's not relativistic invariant. So it's at odds with the theory of relativity. And what Dirac said, okay, I will generalize this equation in order to be, in accordance with the postulates of the special relativity. So he generalized the equation, and he got his famous equation, which has a Hamiltonian, we call the Dirac Hamiltonian. So this somehow is not okay. We have here, and we have here C, a matrix alpha. This C alpha is essentially what plays the role of the velocity of the charge in this Dirac picture. And then we have MC squared, which is the rest energy, and beta, which is a matrix. So these matrices are given here, so this is just tensor products of Pauli matrices, essentially. Now you start with this Hamiltonian, and you do properly go to the limit, to the non-relativistic limit, you will get the Pauli-Schrödinger equation from there, really from scratch, okay? Now, you can get also the magnetic moment, so you want to identify what is a spin. And I tell you before that, if you do this calculation classically, it didn't work, but if you do it quantum mechanically, so it actually worked. So you can use this relation for the magnetic moment, which is essentially given by this cross product of the position and the current that is, if you have a loop current, so this is general expression for magnetic moment generated by a loop current. Okay? And so the current in the Dirac representation on this Dirac theory is given by this expression. So E C alpha, because as I mentioned before, C alpha is the operator for the velocity of the charge. And there is something that is called the Gordon decomposition, where you can actually decompose this expression into two components. So you have an orbital component, which is typically what we know. So this is well known from quantum mechanics. But you get this also, I call it internal here. In many books you will find this like a spin, but it's not really the spin current we are going to talk about. So I don't want to confuse this, so I just will be calling this internal current. Now, so what actually gives the magnetic moment is this internal current. So you see that in the internal current, you already have this sigma matrix, and this sigma matrix is essentially given here. It's the tensor product of the unit, the identity matrix with the Pauli matrix. So it's just a block of, a 4x4 matrix in which each diagonal block is a Pauli matrix. So this is essentially the spin, the Dirac spin. And if you substitute here, you actually will get that, the magnetic moment generated by this loop current, internal loop current, will give you this expression here, which essentially tell you that this spin, this S, this operator here, is the spin density. Right? So from here you get what actually give you the spin. The spin is given by this circulation of this internal current, which generate this spin density. Important here, so the operator for a spin, then in the Dirac picture will be this capital sigma times h bar over 2. So if you do the non-relativistic limit and look, how this operator is changed, surprisingly you don't get the Pauli matrices, you get the Pauli matrices plus something. Okay? And you can see that they are similar, but they are not really the same. And so in many books you'll find, okay, the Pauli matrices are, the non-relativistic limit of Dirac matrices, not so that, okay? So they're actually different. You can see this immediately because you see, if you look at the conservation of these Dirac matrices, or Dirac spin, the sigma, you will see that it doesn't commute with the Dirac Hamiltonian, even in the absence of any field. So the Dirac spin is not conserved, even if there is no field in there. So what is conserved is the total angular momentum. So the sum of orbital momentum plus spin is conserved, but separately they are not conserved, even if there is no field. From the Pauli, from the Schrödinger equation or the Pauli, from the Pauli equation, if there are no fields, the Pauli matrix or the spin, given by the Pauli matrix is conserved. It commutes with the Hamiltonian. Okay, so they are a little bit different. So you may define actually other, and there are a lot of debates about that. You can define also other spin operator or a spin Dirac operator that when you take it into the non-relativistic limit, you reproduce the Pauli matrices like spin operators. This can be done, but it's out of the scope of this course, okay? So, what I went to all these SU2 symmetries because they also provide an elegant way of reproducing or getting the Pauli matrices just from symmetry that you impose, essentially from gauge theory. So, you can get the spin orbit coupling, you can get the Sigma interaction using applying this so-called non-abelian gauge theory. So in a gauge theory, so you probably are familiar with the U1 gauge theory, and essentially the idea is we know that the wave function is defined up to phase, right? So if I have a wave function and I have a new wave function which is differs by just a phase factor, they are equally good. So there are no, you cannot distinguish these two. They give you exactly the same physics. Now this is a global phase, so meaning this phase here doesn't depend on position, it's just a constant. So these two functions are equally good. Now the idea is, well, let's start with this global symmetry, this global phase symmetry, and impose that this symmetry should hold also for the case of local gauge transformation. So, and by local means that this phase here depends now on position. And I can write it conveniently. I put this E over H bar, and so just for convenience. So what you find, and you probably have seen also this in quantum mechanics course, that if you require the Hamiltonian to be invariant to this transformation, you have to pay a price. And the price that you pay is that, okay, you will have to introduce a field, and a field that transforms in that way. So this field A, when you do this transformation, the A has to go from A to A plus this gradient of lambda. And you can also introduce the field Fm, which is given by this, is essentially like the curve of A. And this is the so-called electromagnetic field tensor. And the momentum also has to be changed. Okay. So this, you get it, all of this, you get just from imposing this gauge transformation. This is gauge transformation in just a phase, so e to the power something. This, happen to belong to this U1 group, so they call it a U1 gauge theory. So what you get from there is you start with the Schrödinger equation, or the Dirac equation, you pose this gauge theory, and you get for free the electromagnetic field. So you get everything for an electromagnetic field. Even you can see that you will need the photons to be massless from this theory, just from this gauge transformation, okay? So now the question is, can I use the generator for the SU2 group also to do this gauge transformation? And what I can get from there. So you can do actually exactly the same because you can start with this global transformation. So this is the unit matrix. So obviously, essentially here is like some factor times the unit matrix. So these two functions are absolutely the same or equivalent. So they will give you exactly the same physics. But now you can say, okay, this is a global transformation, so I will impose that this is also valid locally. So you will require that your Hamiltonian will be invariant under this local gauge transformation. And the first part will give you, okay, so this what we already did. So the first part is just the U1 gauge part, so we'll give you electromagnetic field. And this second part will give you another field, which is the spin-orbit coupling field, essentially. And we'll give you new operators for the case of this new field, or this new vector field, and new the analog of this electromagnetic tensor now. It is the spin-orbit coupling tensor, and so on. So you can define this, and you will get, when you do this, when you require this Hamiltonian invariance under this SU2 gauge transformation, you will get actually the Pauli-Schrödinger equation with some extra terms, which are constants, so you can neglect them or disregard them, but it's very elegant. And actually, you can also introduce some covariant derivative. It's very elegant, and also solve some problems when defining spin currents. So unfortunately, I don't have time to go to this in the course, but if you are more interested, so you can go to this paper. It's very well explained more or less in there. So the idea is actually, if there are someone that have been working on particle physics, it's the analogy of what you would do in chronodynamics. It's the same idea, but now with this SU2 group instead of SU3, which is what you have in chronodynamics. Anyway, so any question till now, by the way? Yes?
In the previous, like the sigma, in the SU2, sigma 0 is
is the identity matrix.
Is
Identity, 1, 0, 0, 1. So this is sigma 0, and then sigma x, sigma y, sigma z are the Pauli matrices. Now, so we have a spin, and so how to make a spin relevant? Because if we have a spin, we know that they have these two possible orientations. But if I have the same amount of spin up and spin down, on average, I don't see anything. So I need to break the spin degeneracy in order to distinguish this spin. So we need some way of making this spin relevant. And for this, as I mentioned right now, so you need to break the spin degeneracy. You can do this via the Zeeman interaction, you can do this via spin-orbit coupling, etc. So there are other ways also. So what essentially we need is to create an imbalance in spin up and spin down population. So we need to get different amount of spin up and spin down. So then we will have really a spin that will be dominating. So we'll have a net magnetic moment which is non-zero. So we need to create spin polarization. So then this term spin polarization just means that you will have more carriers with a given spin than with the other spin, right? So you have an imbalance on the number of carriers with a given spin. So we can create this spin polarization by different ways. So intrinsically, say by exchange splitting, I will talk a little bit about this exchange splitting. And we can also use some other tricks like spin filtering, spin pumping, spin injection, spin extraction, etc. So I will go in some details a little bit. Now for the exchange interaction, I have some notes. So I will go through this now very quickly. Not go through all the math details, but I will give you the notes so you can go through the math details. So the math details are done step by step, so you should not have problem doing that at home. Okay, so the exchange direction will create this imbalance of spin, and it is essentially coming from the electron-electron interaction. So if we have, let's say, a couple of electrons, we will have the Coulomb interaction, Coulomb repulsion between these two electrons, right? So the total energy will be then the sum of the kinetic energy of each individual electron plus the energy of the interaction. So this is the energy of the interaction here, is essentially this matrix element with the Coulomb potential, and psi is the two-electron wave function. Okay? So electrons are indistinguishable fermions, so I have to create a wave function that is antisymmetric, as it is for indistinguishable fermion. So the general form, if you have only two electrons, is just to build this two-electron wave function in this way. Okay? Now, all of these components, so these components are spinors, so they are the product of a function which will give you the spatial part, and then the spin or describing the spin, which is this chi function here. So this describes the spatial part, and this describes the spin. Okay, we have two different spins, so that's why we have two electrons. So we have I1, 2 for electron 1 and electron 2, and alpha and beta for the essentially for the spin up, spin down. Okay. Now you can put this two electron wave function into this energy for the interaction, and this is done here. Okay, and at this step, this is just just substituting this equation in here, and then you get this expression. You can work out all these pros here, and we'll end up that finding that this interaction energy is the sum of two direct component and exchange component. So the direct contribution is given by this expression here, and the exchange contribution is given by this expression here. So if the electrons have a positive spin, so they are in a singlet state, their spinors are orthogonal. So the product of chi alpha, chi beta will be 0 because, well, they are orthogonal. So the chain interaction will be 0. But if they have the same spin, so they are in the triplet state, then this exchange interaction is not going to be 0. And you see it's negative, right? So you see that this exchange interaction is negative. So it is 0, is the spin are different, and is a negative number is the spin are equal. So it means that energetically this favor that the situation with the spin have the same orientation. Now there is another thing that you have to take into account is when you start to put more spins in one band, so you have to go up in the energies. So from the kinetic part, you will increase the Fermi wave vector, and it means that from the kinetic energy part, so putting a spin with the same, putting electron with the same spin will not be favorable. But from the point of view of the interaction, it will be favorable. So you have this competition, and if the exchange direction is strong enough, then it can win, and then you can go into a magnetic state. Okay. So the final point is that you end up with an imbalance of, you have essentially more electrons in one band than in the other. Okay. So more electrons, let's say, spin up than spin down. So you get an imbalance on the population of spin. So the model Hamiltonian that you can get from there is this Hamiltonian here. So there is in one of the problems that I have prepared, there is a mean field approximation that you can actually derive all the way down to this equation. But this is what you get in this very simple model. So this is the kinetic energy for the single electron, and the exchange field will give you this splitting. So it just shifts your band one up and one down. So you get more electrons in one band than the other. So how much time do you have?
I think
it's over. Okay.
Yes.
Okay, so let me just go back quickly to. Okay, so that's essentially what you get. You will get more electrons, let's say, in the red band because you have more state, and less electron with the other spin in the purple band because you have there less spin. So you have a spin polarization. More spin up than down, so you will get a magnetic moment. That's what happens with magnets. Okay. So any question?
No question? If not, then let's thank Alex for today. And we continue tomorrow. Again, we are starting 15:20, and tomorrow we have 2 hours. So the continuation is tomorrow, okay? And I'm inviting everyone, so we are having a seminar on the 5th floor today. So Yutin is talking, so she's very happy.
All right, so just so on the lectures, you will probably see that I have to cut because, well, they are not prepared for this. You have one day less time and the other 2. So the cut is not going to be by the end of the lecture. So.
Okay. And I will then get the material and I will upload it to my Moodle site. So everyone who is in the course of the solid state physics will have access to the slides and the handwritten script for the further calculations. Okay? Okay.
Great. Thank you for your attention.
Thank you. Thank you.
You're welcome.
Maybe what is necessary to do? What we need to do with the recording?
Okay, thank you. I have great permission.